Welcome to Module 2. So in Module 2, we're going to derive some equations. So we're going to be talking about one-dimensional motion and a bit of free fall, think gravity, right? So we start with the derivation of a new equation. I'm going to show you the equation. Here it is here. And now we're going to derive it. So they start with acceleration. If you're a math brain, you already know how they got there. But I'm going to demonstrate it for you just so you have it. You don't have to derive these equations for the homework or for the test, but being able to derive these equations will help you to use them better and to remember them. So we know acceleration is the change in velocity over the change in time. We talked a little bit about how the delta means the final minus the initial. So time final minus time initial. But we also talked about how most of our physics experiments are starting when time is equal to 0, so we can simplify this expression as simply over time and not time initial, time final minus time initial. Alrighty, so as you could see in that other equation, they isolated to get this v over here by itself and then a v0, which is v0. So let's talk a little bit about that. We're going to get v final on one side of the equation. So let's go back to where we are now. We're at v final minus v initial over time. Okay. To get the v final by itself, we're just going to do a little bit of algebra or basic math, really. So that's how we get the time out of the denominator and into the numerator. We multiply both sides, it cancels on this side, it stays on the left side. Now time is out of the denominator. And then we want to isolate v final, so we're going to simply add v initial to both sides. So we're left with at plus vi is equal to vf. Now if you look at what they have in their pink equation, it looks different. So, well, first of all, theirs is rearranged differently. They have equated to show that v final is simply equal to v. They just call it v. I don't really like that. I want to call it v final, and I probably will consistently still say v final, but know that v final is equal to v in your book. Okay? They've also taken vi and changed it into v sub 0, which is called v naught. I will use v naught in your book, and the rest is the same. So if we simply convert vi to v naught and v final to regular v, we will find we have the same exact equation. So v equals v naught plus at, and lo and behold, that's exactly what this equation states here. V final is equal to v naught plus at. So you've just derived your first equation. It's in pink. Your book commonly refers to this as equation 2.6. So we have just derived equation 2.6. Okay? Now we can use equation 2.6. You simply plug it into a problem. So here's our equation. Here's our problem. So a car slams on the brakes to avoid hitting an obstacle on the road. We're going to presume, we should make assumptions, but when your book says slams on brakes, it means stops. So the car stops. So it was going, now it's stopped. That means v final is equal to 0, right? The car had a maximum deceleration of 2.3 meters per second. We talked about how we don't decelerate in physics anymore. We simply have a negative acceleration, so that is how we're going to record our deceleration as a negative acceleration. Okay, the rest of this problem says it takes 15 seconds for the car to stop. Well, t equals 15 seconds. Great. How fast was the car initially traveling? There's our question. How fast was it initially traveling? Oh, that's vi, otherwise known as v naught. So we can use our equation. So we have v, which means v final, right, is equal to v naught plus at. Okay, remember v naught and vi are the same thing. They can be used interchangeably. There is no difference between them at all. So we have a v final. We need a v initial. Let's rearrange our equation for v initial. So we're going to subtract at to both sides. So v final minus at is equal to v initial. Okay? So we've put v initial on one side of the equation, isolated. That's good. It makes for more sure math for sure. Put this in parentheses so we don't get our signs mixed up. Alrighty, so we have our acceleration or deceleration and our time. Alrighty, so we can clearly see that this is not going to matter. This is going to become positive because of that double negative. Put it in your calculator and you'll get an answer, and you'll find that v initial is equal to 35 meters per second. Okay, let's use it again and on your own 2.7 or 2.1. So here's the next one on your own 2.1. So in this problem, a car is traveling 35 meters per second. Well, 35 meters per second, that's a velocity clearly. This is the car. I don't know if that's the beginning or the end, so I'm just recording it like that. I'll assign a v final or v initial as I keep going. And it passes a police car which is moving 23 meters per second. Notice I'm making a new column because I have a different object. I don't want to get these confused. That's also a velocity unit, so I'm going to put a v. I don't know if that's v final or v initial, so I'm leaving it like that for now. It's moving about 23 meters per second. And notice it gives you extra numbers, about 51 miles per hour. They're just trying to confuse you, okay? Just stick with the same units. If you have SI units, stick with them. If you don't have SI units, make sure you consistently have imperial units or something of that nature. Stay consistent. So the policeman does not have a radar gun, so he immediately starts to speed up. Well, he's accelerating, isn't he? I don't even know how, but I know he's accelerating. He's speeding up. Immediately starts to accelerate in order to match the speeder's velocity. That way he will be able to measure how fast the speeder is moving. Okay, so think about it, without a radar gun, he is going to use his car as the radar gun. He's going to speed up until his speedometer indicates the speed of the other car. Well, if he does that, he's going to speed up until his speed matches that of the car's speed. You have to read between the lines. So that means his v final is going to match the car. So therefore this becomes our v initial. Okay, we're pulling reason out of the word problem. If the police car can accelerate at a rate of 2.5 meters per second squared, how long will it take the policeman to match the speeder's velocity? So we know we're looking for time. Alrighty? Didn't we just find a new equation to use? Oh, we did. Look, equation 2.6. Let's write it down. So we have v final is equal to v initial. Remember, v initial is v naught plus at. Okay, so I don't want to plug in anything yet. I'm going to rearrange it first for time. To do that, I'm going to isolate time on this side by subtracting v initial to the other side. And I'm going to divide acceleration by both sides. It's going to cancel on the right and hang out on the left. So my equation, which I'm going to push over this way, is going to be vf minus vi over a is equal to t. So I simply divided that a from the right side. It got stuck on the left side, isolating the t. Now I have a nice equation which I can plug in these values into. And that's what I'm going to do. So 35 meters per second minus 23 meters per second divided by 2.5 meters per second squared is equal to t. This all needs to go in the calculator one time. Let's do that now. So here we have our calculator. We're going to do open parentheses. 35 minus 23, close your parentheses, divided by 2.5. everything's entered at the same time, then we press equal. You will eliminate a lot of errors if you use parentheses and keep your calculator going with one equation. That's part of the reason why we rearrange our equation first, so we can put it all in our calculator at the same time to eliminate any silly mistakes. Alrighty, now what's with our units? Hopefully we're in seconds. I'm going to write S in hope, but let's actually solve it. When we're subtracting our units here, that means that we still have meters per second in our numerator, because you can only subtract units. Now in our denominator, we have meters per second squared. When we divide by a fraction, that's the same thing as multiplying by its inverse. Remember that from 6th grade math? So let's take this and do just that. Meters per second times seconds squared over meters. So meters cancels, second in the denominator cancels, as well as an exponent. We're left with seconds. So our units check out. Alrighty, this is our answer. Let's put a box around it. So, next thing, let's go back over to our book. We had fun with our new equation. Now we're going to derive another one. Okay. This is the next equation we're going to derive. This is equation 2.15. Okay? To derive this equation, we're going to start with velocity, okay? So we're going to take this velocity equation and we are going to make it look like this. You can see that is not a far stretch of the imagination. I'm going to start here because, well, I understand that t initial is 0 and it's gone away, left me with t final. So let's just start there. So we have v is equal to displacement over time. Okay? Now look at this. This is new. They're saying, well, if you have a v final and you add the v initial and you divide it by 2, you'll end up with a v average. Well, that's simply the formula for finding an average. And you're like, well, I got that. Well, what if we set this part of the equation equal to this part? Oh, that's fascinating, right? Let's do it. So change in displacement over time is equal to the v final plus the v initial divided by 2. Look, now we're right here. Okay, so let's keep going. Let's solve for time. To solve for time, we got to get it out of the denominator. So we're going to multiply both sides by t. On this side, it cancels out. We're left with displacement equals vf plus vi times t divided by 2, right? We need to get this out of here. Or not that, but we need to get this out of here. So we're going to divide both sides by this whole big conglomerate. You could do it in piece. Let's do it in pieces, just to be clear. I was going to flip and do an inverse of a fraction, but let's just take this 2 and multiply both sides. So now we have 2 delta x is equal to vf plus vi times t. Now let's divide both sides by this here. vf plus vi. And I'm going to keep it in parentheses just to keep myself clear. It leaves the numerator here, gets stuck in the denominator there. So 2 delta x divided by vf plus vi is equal to t. Oh, look. We're right here right now. See? Remember, v is equal to vf and v naught is equal to vi. That's just what we found. Great. Now look, they're going to bring in acceleration next. Now remember, acceleration is equal to delta v over t. We've dropped the delta t because we've realized t initial was 0. Let's isolate for t. So we have at is equal to delta v. We find that t is equal to delta v over a. That's fascinating. What happens if we take this and set it equal to that? Let's take this and set it equal to that. So now we'll have 2 delta x divided by vf plus plus vi is equal to, let's break that down, vf minus vi over a. Oh man, that's so cool. Let's isolate for this vf here. Okay, let's put it together on one side. To start off with, let's get this acceleration out of that denominator. So we have 2 delta x a divided by vf plus vi equals vf minus vi. Now let's multiply both sides by this denominator. Vf plus vi, vf plus vi. Make sure you FOIL it, don't forget. 2 delta x a is equal to v final squared. This minus and this plus makes the middle inner outer cancel. So we're simply left with minus v initial squared. Let's add v initial squared to both sides. And we are left with 2 delta x a plus vi squared is equal to vf squared. You did it. You arrived at equation 2.15. Right here. Vf squared is equal to vi squared plus 2a delta x. Bravo. Good job. You don't have to actually derive these pink equations on the test. This is just to show you where they got the reasoning from. You just have to be able to use this pink equation. So let's do that now. So example 2.2. A woman's driving down the road at 20.0 meters per second. Okay. When she suddenly sees a deer in her headlights, the moment she sees the deer, she slams on her brakes, which means stops, right? So I know her V final is going to be stopping. That must have been her initial. So she stopped. My final stopped. That was her initial velocity. The moment she sees the deer, she stops, which the brakes have a maximum deceleration capacity of 2.1 meters per second squared. We don't decelerate, we negatively accelerate, right? How far did she travel before she stops? Ooh, how far? That's a delta x. Wait, I can't use my old Module 1 equation to find that. Displacement, but I can use my new equation 2.15 to find displacement. See, there's displacement right there. So let's record that equation on our sheet. Here. V final squared is equal to V initial squared plus 2a delta x. If we're solving for delta x, we need to isolate that here. So let's do that first by subtracting V initial to both sides. So we're left with V final squared minus V initial squared is equal to 2a delta x. Now let's divide both sides by 2a. Leaves the numerator on the right, gets stuck in the denominator on the left. So we're left with V final squared minus V initial squared over 2a is equal to delta x. We can simply plug in our values now. So V final, 0 meters per second. We have to square it. Minus V initial divided by 2 times negative 2.1 meters per second squared. Equal to delta x. Let's look at our units. We have, we'll look. See this square here? You might want to put these parentheses here to know that it's not just your second squared. It's not an acceleration unit. Okay, you got to distribute that square to both of these. So if you're looking at your unit, well, let's do the math, then we'll go back and do the units. So we have it nicely arranged here. We can simply plug it in. 0 squared minus 20 squared. Okay, close parentheses, divided by 2, we might put it open, 2 times negative 2.1. we find our answer to be about 95. I don't know what my significant figures is, so I'm just going to leave it there. If I'm doing displacement, I know I need to be in meters. Now let's make sure we are. So here we're at meters, and see that square? That means meters is squared and seconds is squared. And that's the same units for this and this, which is good because you're subtracting. They have to be in the same units. And we're dividing here by meters over seconds squared. Remember, when we divide by fraction, it's the same thing as multiplying by the inverse of the fraction. Okay, second square cancels, this cancels, we're left with meters, so our units checks out. So now you know how to use your new fun equation. For homework, I want y'all to do Module 2, sorry, I flipped some pages, 1 through 3, try to get there. Okay, so Module 2, practice problems numbers 1, 2, and 3 on page 70, okay?